My socks feel dirty. Give me some water to wash them.
Again, Homer, we have to ration the water carefully. It's our only hope.
Oh, pardon me, Mr. Let's Ration Everything. But what do you think we're floating on? Don't you know the poem? Water, water everywhere, so let's all have a drink.
Homer, no!
Quote, "In the beginner's mind, there are many possibilities, but in the experts, there are few." End quote. That's from Shunri Suzuki. Sometimes something is so ordinary, ubiquitous, and seemingly dull or scientifically passé that we fail to see the mysterious beauty before us. Even though we rely on this perplexing substance for our existence, we, the average public person, do not search for answers. We don't even know if there are any questions to ask. Sometimes, as Suzuki tells us, it takes the ability to look at the world from a beginner's mind to realize that even experts are lacking something. Sometimes we miss the mysteries or magic simply because we've always been surrounded by it. Welcome to episode 8 of Remedial Polymath. Water. You don't know about it. Let's start with a story. Tanzania, 1963. The yoke of British colonialism had recently been lifted. America was in the midst of figuring out how to get men on the moon using machines containing far less computing power than many modern watches. The Beatles were about to change popular music forever. Unthought of weapons such as the hydrogen fusion bomb, that is an atom that is pertinent for our discussion, colloquially known as the H-bomb, hung over the heads of almost everyone. We eagerly looked to realize so much novel information about our possibilities, our world, our solar system, and beyond. And it was happening. We were excelling in a manner unknown to humankind before that time. And just as how at times one can't see the forest for the trees, at times we can't see the trees for the forest, or maybe not even the soil beneath both. Because when it came to the substance that envelops most of our planet, which we consume and interact with daily, we apparently have so much to learn. We didn't know things, not to this level, about the substance we call water. That was in 1963, and guess what? We still have a dearth of knowledge about this necessary molecule that makes up 60% of our bodies. Yeah, 60% of you is water. That is mind-bending if you stop and think about it. All right, back to Tanzania. A 13-year-old boy named Erasto Mpemba was in his secondary school making ice cream in a class. Each student in the class was mixing boiled milk and sugar. Usually you wait for the mixture to cool before you refrigerate it. Mpemba got bored and decided to refrigerate his mixture right away. Soon, he checked his ice cream and was amazed that the time it took for his bag to become ice cream was quicker than any of his classmates who had waited for theirs to cool. When he presented this surprising phenomenon to his teacher, he was disregarded, laughed at, and almost shunned away. He was told this observation couldn't be possible. But Mpemba knew what he witnessed and wasn't satisfied with this dismissal. He may have been bolstered by his findings from local ice cream vendors who were more familiar with this phenomenon. Mpemba held onto this memory and his assertion. 6 years later, a physics professor visited his school. His name was Dr. Dennis Osborne. Mpemba asked him bluntly during a Q&A why hot water freezes faster than cold. Again, he was chuckled at. Osborne was taken aback, but upon hearing this question, he decided to give the boy his attention. He probably also just had to know if this could be correct. So they ran experiments, freezing beakers of water at different temperatures simultaneously. To that doctor's surprise, Mpemba was correct that the hot water in their experiment froze quicker than the cold water. It took until 1969 for someone to formally notice this and present it scientifically. Their findings were then presented in an article in the Physics Education Journal, where they were both listed as authors. Like how gravity pulls on objects of different masses at the same speed, these observations don't compute with our instincts. Even experts often don't think of overriding those instincts. We collectively never even look into questions like this until someone throws some objects from a leaning tower in Pisa and does a straightforward experiment. That was Galileo, by the way. We now call this water temperature phenomenon the Mpemba Effect, and we know that it does indeed happen often. But astonishingly, until this day, we have yet to understand precisely why. There are many theories and many detractors, but no explanation has reached a consensus. That is what is fascinating. Not so much the scientific facts as that simple truth about a quote-unquote simple substance. It's still hotly debated. Perhaps even more astonishing is that Aristotle and René Descartes made vague references to this effect, without explanation, of course. So, even with two incredibly respected scientists/philosophers in our history, even with them making references to this potential phenomenon, no future scientist decided to run an experiment. Humans could just not overcome what they thought was an obvious occurrence. That is until a curious Tanzanian high schooler, unburdened with the domestication of science, decided that he wanted his ice cream faster. It took the mind of a beginner to challenge the experts. Because of that, we scientifically established something previously unknown about the most common liquid on Earth. Now, it should be stated that the Mpemba effect is not universally accepted and lacks a definitive scientific explanation. It does not always occur, especially in highly controlled scientific environments, such as having the water containers in a vacuum where evaporation wouldn't happen. But of course, we don't live in a vacuum, and in many everyday situations, it certainly does occur. You may have seen videos of people throwing water into the air when it is extremely cold out, and it freezes before it hits the ground. That is done with hot water, not with cold. And I have read that, quote, further research is needed, end quote. That's the fantastic part. It's 2024, and further research is needed to understand water freezing. Nevertheless, it's a stellar and fitting story. So, let's be like Erasto Mpemba. Be curious and examine this beautiful life-giving molecule. There is so much we need to learn, and even more in which we can scientifically tell the what, but not the why or the how. Either way, I'll wager you've never been exposed to this information. I certainly was not. When you realize you're surrounded by magic and mystery in your everyday life, that's a fun topic worth exploring. And what's more everyday than water? If you're still listening to this episode, I would like to think you at least don't hate the show. The purpose of this show is to give you all a little bit of fun and wonder while we explore a variety of topics. I aim to challenge you while keeping it accessible. I do this for everyone by doing a lot of researching, reading, writing, and rewriting. There's currently no money in it, so I ask in return for you to take 10 seconds out of your day and rate and review it on any podcast app you use, but especially if you use Apple Podcasts, even if your review is just good show. If any topic or episode is to your liking, please share it on any social media app or website that you fancy. I need your help in this regard. But even more importantly, could you tell those in your life about the show if you are enjoying it? Nothing beats word of mouth. You listeners who have found the show while it is still just a baby, I love y'all. Any and all assistance is deeply appreciated. Okay, back to discussing water. Let's dive in and make our way to the deep end of this pool. All right, now here's the formal introduction. Despite our utter dependence on it, water is a puzzle. Scientists don't understand precisely why it expands as it cools, why hot water can turn to ice faster than cold water, or its extraordinary surface tension which allows it to cling to soil and even support insects. Quote, "It's almost like water is trying to hide its secrets," end quote, says John Russo, a mathematician at the University of Bristol in England. who thinks he may have figured one of those secrets out. Quote, "The structure of water, the reason for its peculiar properties, is a major question in chemistry and physics," end quote. That's from Richard Sekali from the University of California, Berkeley. But let's back up a little bit. Water has slightly different meanings in different languages and cultures. In some, the word unsurprisingly also means life. In others, it also means flow. In others, it is the same word as rain or river. Its importance and secrets to our ancestors means its definitions sometimes jump meanings. For this discussion, we will steer towards discussing water as the H2O molecule, instead of large water-related systems. That being said, my favorite different meaning for water is flow. That was in Sumerian, where this word was also used for the number 1 and the letter A, although that wasn't the first letter as we think about the alphabet. Still, that is bewitching information from one of the oldest civilizations we know of. Because of Earth's average temperature, water's liquid form is the most common, although we know it can easily transition into a gas or a solid through temperature changes. The clouds we see in the sky are just water in a different form. The ice in your fridge is it's also water in a different form. I know, that's no surprise. Just stay with me. Those of us in developed countries often experience it in all its forms daily without thought. We know we need it to live, sure, but we think about it little more than that. I haven't yet told you anything you don't already know. Did you know that of all the naturally occurring liquids on our globe, it effortlessly makes the world's winner's podium for the strangest? It acts in many ways unlike anything else. Plus, this isn't just curious. If water wasn't so bizarre, we wouldn't be here. Human life and most earthly life in general wouldn't really be possible. The substance life requires to fend off death can only support life due to it being so anomalous. Do you believe I am now being ambitious and hyperbolic for the sake of podcasting? Well, maybe, but this episode will just scratch the surface. We will keep this quote-unquote simple. It could have been much longer, but I wanted to mix things up from the last couple of topics. Consider this. When compared to most other liquids, scientists tell us water has 66 properties that the vast majority of other liquids do not possess. We will not explore all of water's 66 wild properties. Do not worry. But let's take a look at some of the prominent ones. Where does it come from? One should begin at the beginning, of course. Where does our water come from? For Earth, it is improbable that, like most else on our planet, the entirety of our water is from the initial planetary formation. Not entirely, at least. When our planet was more akin to a ball of lava a bit over 4.5 billion years ago, it was a sweltering place without an atmosphere. If any water was within that fiery ball, it may have just been vaporized or volcanically ejected, which would have led to it being blown into space by the solar wind from our sun. We could have had the precursors for water, hydrogen and oxygen, of course, but again, the water would have become a gas right away and been blown away from the hot protoplanet without an atmosphere. Once the Earth cooled, there could have been some beneath the Earth's crust that found its way out, but that doesn't explain the vast amount we witness today. We are left with a water delivery system, which is still out there, but was much more common at this stage of our solar system, namely comets and asteroids. All right, to cut to the chase, from testing the ratio of heavy hydrogen, that's the hydrogen with the proton, within asteroids to the water on Earth, we see that they match up well. Much better than the water from comets. even though we can't 100% rule them out either. So asteroid impacts post-Earth cooling best explains why so much water is here. It may also help explain why Venus and Mars do not show as much water. They were not treated to the same collection of soggy asteroids. You may have heard that you are made of stardust, and that's true. Everything in our solar system comes from the explosion of what existed before our sun. But Earth's water, or water ingredients, seems to come from an asteroid or two visiting our planet after it cooled down. So while most atoms in your body may be from a solar explosion, it seems that almost every molecule of water, which is 60% of your body, comes from asteroid travelers to our planet probably billions of years ago. This is interesting because I knew Earth was the right size, with the right ingredients, at the perfect distance from an ideal type of sun. It wouldn't have been enough. We also had to be hit with the right asteroids at the right time. To say our home planet is lucky or unique is to do a disservice to those words, as we're light years beyond the meaning of those words when describing the anomalous planet we come from. Was the water only from asteroids? Probably not. But would we have life on Earth without asteroids? Probably not. All right, now we're going to start to explore water's weird ways that we can kind of explain. But first, we got to just explore what is water. Let us now discuss something a little close to Earth. Let's examine first simply what water is. I don't have to tell you that water is 2 hydrogen atoms and a single oxygen atom. Oxygen has 8 electrons, the negatively charged particles that orbit the center of an atom, and hydrogen has 1. When they meet up, they create a letter V of sorts, with oxygen at the bottom of the V and the hydrogen atoms at the top. The hydrogen atoms grab an electron from the oxygen atom, and this holds them in place as a molecule. This is called covalent bonding. We'll come back to that a little bit later. Sidebar. Is it not wild that if you separate water's 2 components, hydrogen and oxygen, you are left with gases that, when combined with a spark, will lead to massive explosions? But of course, when combined into water, you have a molecule that can put that flame out. Just find that interesting. All right. In H2O, the hydrogen atoms have a very strong covalent bond with the oxygen atom. Through the sharing of electrons, they both fill each other's electron shells, which we don't have to go into, just know it's a powerful bond. These hydrogen bonds are attractions of electrostatic force caused by the difference in charge between slightly positive hydrogen ions and other slightly negative ions. Again, it's not essential to understand that. Just know that, in short, water molecules are also attracted to each other. This hydrogen-to-hydrogen attraction has some interesting and unusual side effects. All right, another sidebar. It is actually the strength and regularity of the hydrogen bonds that keep water from being a gas at regular atmospheric pressure and in typical ambient temperatures here on Earth. In contrast, hydrogen sulfide, ammonia, and hydrogen chloride are 3 light molecules like water, but at room temperature, despite being similar to or greater than water in weight, do not have hydrogen bonds as effective as water does, and hence they are gases at normal atmospheric pressure and temperatures on Earth, and water is not. All right, stay with me. Now, let's examine the shape water molecules like to take when put together in their liquid state. The hydrogen atoms in a water molecule can be hydrogen bonded with up to 4 other water molecules. I have heard this described as 4 V's attached to each other. Basically, it's a 3D pyramidal shape with 1 molecule in the middle of the pyramid. The formal name is a tetrahedron. This is not a common occurrence. And while we understand how it's done, we don't know why, as other liquids do not behave like this, even with similar properties. All right, one last sidebar. It's fascinating that the molecules of the liquid water we need to survive take the shape of a pyramid. It forms itself into a shape that has always fascinated mankind. The shape of some of our older and most mysterious structures that are found on every continent. Did the ancients know something somehow that we've forgotten? That's half joking. But I'm never one to put such symbolic mystery past our ancestors. Either way, what a fun coincidence. All right. There are other polar liquids with hydrogen bonds, like we talked about, ammonia, ethanol, hexane. However, they do not form the extensive and highly organized tetrahedral network we see in water. There's an interesting addition. The hydrogen bonds between H2O molecules are clearly weaker than the covalent bonds within H2O. They're about 10 times weaker. This means that the attachments between the hydrogen atoms, they can form, break, and reform quickly in liquid water. But much of the way they break and form holds many of the mysteries of the substance of water in general. But just remember that. There'll be more on this later. So what did all this mean that I just said? All right. So while 4 liquid water molecules like to join together into this 4-sided 3D pyramidal structure, there can also be others with 3, 2, or no bonds with other water molecules. The number of hydrogen bonds formed per molecule varies, and that can vary depending on what the water is doing. This ability to create complex hydrogen bonds between the water molecules without guaranteeing the complex hydrogen bonds is not common. Okay, I threw a lot of science at you, and you'd be forgiven if your eyes glazed over a little bit. The important thing to realize is that water molecules are very attracted to each other, and they like to form into a shape known as a tetrahedral, but they don't have to. They can form in different ways in liquid water. That is unique, as well as the strength of their hydrogen bonds. But, okay, let's move on. Let's discuss what are these odd rules that H2O plays by really mean for us and our world. Another interesting attribute of water is that it is super sticky. Formally, we say that it has a high amount of surface tension. Actually, it has a ridiculous amount of surface tension. We've all witnessed this, but may not have given it much thought. This high amount of surface tension is why bugs can walk on the surface of water, and even a paperclip will float on water if it's correctly placed. Okay, bugs and paperclips aside, what does this mean for us? That's a good question. This surface tension allows water molecules to flow through the smallest blood vessels in the human body, even when fighting against gravity. It means that the water is grabbing oxygen, nutrients, and the like along with it. It allows for plants to suck up water from deep down within the ground. It allows the soil to easily retain water, making it available for any type of plant for a relatively long time. Those are attributes for which we should all be thankful. The stickiness of water also plays into, but isn't solely responsible for, water's incredible weight. Water's density is relatively off the charts. The same hydrogen bonds that help make water so sticky also lead it to being so dense and weighty. Think about it. A gallon of water weighs in a whopping 8.5 pounds, or around 3.8 kilograms. This also leads us to another interesting and unique fact. Water is incompressible. Its volume doesn't change under pressure, even immense pressure. Whether you are at the surface or visiting the Titanic, the weight versus volume stats for water are essentially unchanged. Not only is that just fascinating, it also means that water retains its density across any conditions. Just think about how useful this fact has been for us humans. It means we can load up a ridiculous amount of heavy material or a serious amount of people onto relatively little boats and move them easily to where they need to get. Just think of a U.S. aircraft carrier. They weigh around 100,000 tons, and yet they float not only easily, but with plenty of height to spare. You know, the part that's out of the water. Usually having a deck above water equal to a 20-story building. This weight of water also helps us with hydraulic power, water distribution systems. Think about those water towers you've seen while driving on the interstate. It also means that water sinks down to aquifers and groundwater for wells, for people, and for farms. Also think about the fact that it assists with erosion and soil fertility, which is a process that fertilizes our farms and shapes our landscapes, forms deltas, forms valleys, and just other landforms that are beneficial for human settlements. It is often unthought of, but we are really blessed that water is so heavy. Universal solvent. Another interesting attribute of water that is almost as important is that it is an excellent solvent due to its hydrogen bonds and interesting shape in liquid form. It doesn't just stick to itself well, but to almost anything else as well. This means there is little competition when it comes to tearing other compounds apart. It's virtually a universal solvent. Nearly every compound we know of will dissolve in water, at least slightly, which is wild if you stop and think about it. It's probably the best solvent we have on Earth, so much so that it becomes challenging to create absolutely pure water, even in a lab setting. Think about that. There's pretty much always something floating around in there. This ability to be an amazing solvent is crucial for life. Nutrients and oxygen can reach where they are needed in our bodies, and poisons that need to be ejected from our bodies can all move to where they need to go because water can dissolve and easily transport them. Our DNA and the membranes of the cells within our body won't work without water. And it gets cooler than just its ability to dissolve other things. DNA and its double helix couldn't exist without water, and its surface is always covered by water molecules. But I think it would be better to quote from an article from Science Daily on water and DNA. Quote, "The DNA's double helix never occurs in isolation. Instead, its entire surface is always covered by water molecules, which attach themselves with the help of hydrogen bonds. But the DNA does not bind all molecules the same way." Quote within a quote, "We've been able to verify that some of the water is bound stronger, whereas other molecules are less so." End quote within a quote. That's from Dr. Harman Fahmy, head of the Biophysics Division at the Institute of Radiochemistry. This is, however, only true if the water content is low. When the water sheaths swell, these differences are adjusted and all hydrogen bonds become equally strong. This in turn changes the geometry of the DNA strand, the backbone of the double helix, which consists of sugar and phosphate groups, bends slightly. Quote within a quote, "The precise DNA structure depends on the specific amount of water surrounding the molecule," summarizes Dr. Fahmy. Okay, end of the whole quote from Science Daily on water and DNA. Okay, so what does that all mean? It means our DNA's exact shape depends on how much water is present. Not only do your organs and body need water, but your DNA's geometry will change without it. I know this may be eye-rolly, but I didn't just say we need water. We are so intertwined with it that without it, in a short time, the geometry of our DNA changes, and the DNA seems to start making decisions about which part of itself needs water more than others. That is straight trippy. I've never heard a better argument for hydration than that. Water and heat. Another interesting side effect of the tetrahedral shape of liquid H2O and the bonds within it is water's fantastic ability to hold onto heat. This in turn is why water is an excellent coolant and why it has been used to cool down everything from nuclear reactors to planes and cars to servers and data centers. So while it can absorb a lot of heat, it also takes a serious amount of heat to actually change the water's temperature. And then in turn, it can take a long time for that water to cool down. When water is exposed to heat, that extra energy goes into converting more and more molecules from its tetrahedral shape to other more disordered structures. So the heat doesn't go immediately into kinetic energy, meaning its temperature, but the heat goes into a change of the water's molecules' shapes, at least at first. So water is exposed to heat. It won't just immediately go up in temperature. It will start changing the water molecule shapes. This is not a common reaction for a liquid. For this reason, water also has a very high boiling point compared to other liquids. This plays a massive part in explaining why Earth is the way it is. It means the oceans take a long time to heat up and a long time to cool down. This, in turn, means that they play a significant role in being a moderator of sorts for our climate. This is why, on balance, areas near the oceans rarely get very hot or very cold. On balance. It is why the Gulf Stream works and why Northern Europe, latitude-wise is almost the whole of Europe, is currently as warm as it is. This is why, despite Chicago and Barcelona having a similar latitude, they couldn't have more different climates. The Caribbean is a long way from England, yet the Gulf Stream ocean current stays warm enough to have a massive impact on the weather there. Oceanic currents such as this around the world are vital for moving heat and regulating temperatures. The manner in which water absorbs heat also leads to stable evaporation instead of water solely increasing its temperature through increased kinetic energy like other liquids would do. This means that the water in the oceans can deconstruct the molecular forms within it without ever getting anywhere near boiling. It can then release those non-connected water molecules into the air, with the water barely changing in temperature. This phenomena is again due to the unique pyramidal shape in which H2O molecules like to arrange themselves. This unique aspect of water means we have abundant clouds, humidity, and precipitation, even if you're far from a body of water. Of course, these weather effects make it possible for the weather to be regulated almost everywhere and for fresh water to fall from the sky as rain, which practically every terrestrial living creature relies on. All in all, the ability of water to retain heat and not change too quickly in temperature is why we have, for the most part, a stable and diverse ecosystem all around the world. Sidebar: this is not me saying that we have a stable and diverse ecosystem everywhere or that global warming isn't a thing. With the massive temperature changes via the sun the Earth experiences, looking at everything relatively, no other liquid would keep things as stable as they are here on Earth. Most humans, wherever they are, collectively live within a temperature range that is only about 50 degrees Celsius. That isn't a large number, and this is all thanks to water's properties and its interactions with heat. Liquid water versus ice. Now it's time to discuss one of the most significant mysteries surrounding water, which has massive implications for life on Earth. And it's also my favorite one. It is the trait of water that has always fascinated me and inspired this episode. Water, when it freezes, expands. There are very few liquids of any kind that expand upon freezing. Water is the only commonplace liquid that does so. While we generally understand the mechanism of this phenomenon, we do not have a good idea of the why behind it. Thank God water is out in this way, though. Otherwise, I wouldn't be here talking to you right now. and you wouldn't be listening. Anders Nielsen is a chemical physicist who works at Stockholm University in Sweden and Stanford University in the US. He says, quote, "If you look at the simple thermodynamic and kinetic properties of liquids, as you change pressure and temperature, they all behave the same way." End quote. You see, usually, as you cool off a liquid, its density will increase, and its heat capacity and compressibility will decrease as you near its freezing point. Anders then tells us, quote, "Almost all liquids on the planet behave like this, except for water," end quote. But here's an almost funnier aspect of the story. Water does kind of do what other liquids do. As you lower the temperature of, let's say, room temperature water, its density will increase just like other liquids. This will happen until you hit 4 degrees Celsius. And then bam, just like that, water reverses course and decreases in density. Why 4 degrees? Why reverse course? It's yet to be 100% known why H2O plays this trick on us. And then, when it hits 0 degrees Celsius and freezes, it will be decidedly less dense than liquid water of any temperature. What does this mean? Well, numerous things. Primarily, though, this means that frozen water weighs less than liquid water. It'll float. As to the theories behind why, we will get to that eventually, but first, let's consider the implications behind this phenomenon. All right, another one of my sidebars. I must relate another terrifyingly odd aspect of water freezing. Not so much as to illuminate the implications of water expanding its way into ice within our lives, but just to weird you out and again showcase how peculiar this liquid of life can be. And if you don't feel that God, Providence, or the universe, whatever you want to call it, is essentially winking at us with this substance, consider this. We all know that water freezes at 0 degrees Celsius. That is why it's 0 degrees. However, technically 0 degrees Celsius as a freezing point. That is water with any impurities, i.e. all natural water on Earth. However, that is not the case if you were to get yourself truly pure water. Should you find yourself with truly distilled or purified water, like that from reverse osmosis, then this whole 0 degree thing falls by the wayside. This is when you are dealing with what's known as supercooled water. Supercooled water. The arrangement of the molecules of liquid water determines its state of matter. We can say that the water is liquid when H2O molecules are not touching and they're flowing freely. The water only becomes ice when the molecules come together and they lock into place. But it needs help. It requires some impetus to, quote unquote, lock into place and freeze. It needs something to crystallize with. It needs what's known as a seed crystal. Without a seed crystal, the water has nothing to form a crystal around. It is as if liquid water doesn't know how to crystallize without some impurity or movement. So it stays as it is. Any kind of impurity or even movement of the water could set this off and it will freeze into ice. But as there's never water with no impurities found naturally, this isn't an issue. I know it's bizarre, but of course, with science, we can get pure water and lower the unmoving pure water well to below 0 degrees. This water can go down to negative 48 degrees Celsius before it'll freeze. That is with a completely perfect experiment, as the exact freezing temperatures depend on the shape of the container and its purity. But often other supercooled water will get to negative 20 degrees before it'll freeze. Even just simply disturbing the molecules by shaking, pouring, or banging on a surface can catalyze the crystallization process as well as introducing any impurity. I remember a chemistry experiment that we did in high school. We had supercooled water and dropped an extremely small stone, just almost like a speck of sand, into the container. And then bam, immediately everything became ice. And I'm talking about like within under a second. It's just bonkers to witness. And we will discuss why this may happen for water when we discuss why water may expand upon freezing. For now, I just wanted to weird out anyone unaware of supercooling water. And if you did, I wanted to remind you and everyone of how terrifically odd our life-giving molecule really is. All right, gotta love it. Now the sidebar is over, and we will get back to our regularly scheduled content. All right, back to ice being less dense than water. One would venture to think most humans have never wondered at this occurrence. Ice floats in our drinks. One must remember not to put a water bottle in the freezer. It'll explode. This aspect of water is just a known part of our lives, but honestly, it's downright spooky. Consider other solids versus their liquid form that you've probably witnessed. Does solid wax float on melted wax? Have you ever witnessed solid butter floating on melted butter in a hot saucepan? What about fondue with cheese or chocolate? When you heat it up, do they float at the top of their liquid version? All right. Consider it as the Ice Age, and ice sank instead of floated. It doesn't have to be the Ice Age, but it's more fun to go extreme, to hammer home the point. Eventually, Earth would have moved out of the sweaty dinosaur times and into a colder period for one reason or another. We've plenty of proof that this would have to occur eventually. Ice would be created on the surface and sink. This wouldn't stop. Layers of ice would slowly sink and accumulate on the seafloor. This would just continue and continue. There are many effects that this would have on the planet. First and foremost, eventually, it seems that the oceans would become one massive ice rink, outside of some equatorial regions, maybe. But who knows? Once you have a runaway ice formation, who is to say that even at the heat of the equator, it would be enough to counter the freezer-like effect of the rest of the world, the rest of the oceans becoming ice? We could be relatively sure about this for a few reasons. There would be massive insulation loss. Normally, floating ice insulates the water beneath it. It moderates the water temperature beneath itself. This would be lost if ice sank. There would be a heat transfer issue. The cold air above would cool the water more efficiently without the insulating ice layer, helping to counteract any warming effect from the sun. This would probably create a feedback-like loop that would significantly impact our global climate. The heat exchange between air and water would be altered substantially. This would probably make for much longer ice ages, or ice age would just become the normal. Clearly, we can't know for sure, and just as clearly, this would have horrible implications for life. It is challenging to imagine human beings, not to mention any significant land-based animals, evolving to their current state. This cannot be stated outright, so I'll state it quasi-outright. We won't happen. Let's glance over some other predictions about the planet and the life on it if water didn't expand when frozen. Aquatic life would have it bad. Not only would they lose the insulation that floating ice provides, but they would, in most places at least, just flat out be pushed out of their neighborhood. All the way from tiny plankton, and listen to the episode on seafood to see how massively important those little guys are, from plankton to massive whales. It may not be as big of a deal, but any type of life that requires floating ice, such as polar bears, seals, and penguins, they would have a tough time existing and evolving at all. Global freshwater systems or availability would have to be drastically different. The distribution and availability of fresh water would be entirely dissimilar to what we experience now. If the Ice Age glaciers never receded, we wouldn't have many of the lakes and river systems we know of. If water is ice almost everywhere, there is less liquid water to evaporate, which happens easier at warmer temperatures, and less water ever becomes clouds or rain. There would be no or drastically less rainwater worldwide if the temperature never got warm anywhere. Who knows precisely how it would play out, but it is pretty safe to say if ice sank and remained frozen on the ocean floor, there'd be a lot less fresh water, which would affect the evolution of all terrestrial life. You'd have to imagine it wouldn't positively impact the evolution of life in any way on this planet. Listen, I like to think life finds a way, because that is what we witness around us. However, it is just such a massive stretch to think that with ice not expanding, we ever have a world in which let's say post-dinosaur death from an Earth-cooling asteroid, small moles evolve into larger mammals that evolve into savanna roaming bipedal humanoids that evolve into Homo sapiens. As an article at reptileknowledge.com put it interestingly, quote, "Thus, ice floats because we are here to witness it floating," end quote. This implies a philosophical idea similar to a conclusion I have come to after learning about our life molecule. That is, the physical laws and properties we observe, such as ice floating, are inherently tied to our existence as observers. In other words, the universe must have the properties it does because otherwise there wouldn't be observers to notice and question these properties. Water, at least for life as we understand it, must have these odd properties for intelligent life to exist and bear witness to these odd properties. I feel that water and its workings are another way the universe winks at us. It is the liquid that is the exception that proves the rule. This exception breaks the rules to ensure our universe is tilted towards creating intelligent life, at least on our orbiting rock. Sidebar. We could explore all day how water is unlike other liquids or how H2O is unlike other molecules. Remember, there are reportedly 66 ways water is scientifically unlike other liquids. We touched upon some of the big ones. Now it's time to examine a theory behind why water may possess some of the wild traits that it does. It is the potential why that has been mentioned before in this episode. I love to explore this one, and it's a good topic to end on. Not only may it be a reasonable explanation, but it also invites more philosophical thinking about life, human life, and the way the workings of the universe are embodied in water. I can't help but explore examples of when science and philosophy have a crossroads. Chaos and order. Let's review some of what we discussed near the beginning of the episode. A water molecule can be compared to the letter V, with the oxygen atom at the bottom and the two hydrogen atoms at the top. The hydrogen atoms and the oxygen atom share some of their electrons, which are negatively charged, creating strong covalent bonds. The oxygen atom attracts the shared electrons more strongly, making that side of the molecule slightly negative and the hydrogen side slightly positive. So you have a minuscule magnet now, ready to connect with other molecules like itself. Water seems to like to link up, especially as it cools, because each molecule is attracted to its four nearest neighbors using this magnet-like effect. The resulting shape is a three-sided pyramid, or a pyramid where each side is a triangle, which is the shape we previously discussed, a tetrahedron. And again, there's one molecule at the center of that pyramid. Not only is this interesting, but it's such a beautiful shape. It is also fascinating how it completely embraces the number 3, triangles, and pyramids, which have fascinated humans for time immemorial. I realize that may make many of you roll your eyes, but roll away. It's interesting nonetheless. But I digress. While water's ability to arrange itself into the shape is well understood, what happens after that is not totally agreed upon. In researching for this episode, it was wild how much very educated people disagreed on the reasons behind water's wild behavior, and to what level they disagree. It's utterly fascinating. It reminds me of parts of studying astrophysics in which it seems that at a certain point, one's personal philosophy plays a part into how one thinks about how the science plays out. When Anders Nielsen, who's the chemical physicist from Stanford, addresses this, he says, quote, "The science of water is bringing out very strong, almost religious opinions among different scientists," end quote. Let's try to understand what the issue is. Water has hydrogen bonds, which are relatively strong and directional. As Martin Chaplin, a chemist and water researcher, yes, that's a thing, from London South Bank University in the UK said, quote, "It's a lot of hydrogen bonding for such a small molecule," end quote. And while water behaves relatively similar to many liquids when it's warm, The biggest mystery is why it changes so much when it cools. This is when the hydrogen bonding starts to make a significant impact. Chaplin says hydrogen bonding, quote, actually forces a structured, ordered state, end quote. Now, this is rare for the vast majority of liquids. Usually, the molecules are constantly rearranging in a liquid, not water, and it's because of the hydrogen bonds and the propensity for arranging into a tetrahedron. But it doesn't have to be organized into a tetrahedron. That's not a rule per se. As we touched upon earlier, you can have molecules of water that only attach to one other molecule, or two, or three, or none. There can be many single molecules of water, or even molecules that arrange into tetrahedrons, but do so in a less structured and interconnected manner. For this reason, many believe that water can, in essence, be considered two liquids in one, or to put it more correctly, the molecules in water can exist in two phases at once. I know. Just bear with me here. The main difference between the two phases is thought to be the hydrogen bonds holding the molecules together. In one, 4 water molecules are arranged in an organized and symmetrical tetrahedron. In the other phase, the water molecules are disordered and interconnected differently, and often incompletely. They also have different densities. The low density version is the tetrahedron, which is less ordered and ice-like. The higher density one is with water molecules floating around in a non-structured way. And these molecules have a higher packing ability. All right. Let's not get too bogged down in the science here. The critical part to understand is that in this theory, the water molecules of water essentially arrange themselves in two ways. One is more orderly, and the other is more chaotic. And while this idea has gotten a new boost with modern tools and computing power, surprisingly, it isn't new. There was a German physicist, Wilhelm Röntgen, and actually he was the one to discover X-rays. And he, in 1892, proposed that water was made up of two distinct phases that coexisted in a mixture. He came to this conclusion using X-rays somehow, and while his reasoning has been found to be incorrect, the theory has never left us. In the 1990s, the two-phase model of liquid water got a new boost as computing power increased, allowing scientists to attempt to replicate the actual odd behavior of water. These computer models would change aspects of water molecules to see what effect it would have. Importantly, they would change the strength of the hydrogen bonding that leads to its tetrahedral shape. John Russo, a mathematician at the University of Bristol in England, tells us that by doing this, quote, many anomalies will essentially disappear. You can essentially make water behave like a simple liquid, end quote. In one example in which they altered the strength and shapes of the hydrogen bonding, he tells us that ice indeed became denser than water and sinks instead of floating by increasing water's tetrahedrality. The proportions of water molecules perfectly aligned with its 4 nearest neighbors. And now we know how important that is for life on Earth. So it seems that Rousseau is proposing that without the chaotic side of water, we probably wouldn't be here. So digest that interesting little idea. In this hypothesis, the proportion of orderly tetrahedrons to more chaotic ones, or even just unorganized molecules, it changes with temperature, with more low-density water forming as temperatures decreases. This results in a sort of competition between the increase of density with decreasing temperature and the formation of low-density water. This could explain why water's density maximum is 4 degrees Celsius, in addition to many of water's anomalous properties. But here's the wild thing. It's still a hypothesis. Many scientists and researchers disagree with this idea. Many believe that water can only exist in one phase at a time, and that this is just flat out not how liquids operate, even for one as weird as water. They think that the answers to water's anomalies have yet to be found, and that we may need better technology to find the answers. And that just blows me away. There's a good chance we may master quantum computers before we understand water, the most abundant and necessary liquid on Earth. However, I like the chaos and order theory. Now, I am in no position to have an opinion on this matter. None. Yet, I still do, and I'll talk to you about it. And this is where the philosophy behind the science comes in for me. We've established that water has wild properties that are not understood. Yet those wild properties make water life-giving for people specifically and life-giving for Earth in general. It makes sense to my mind that the reason beneath water's beautiful properties is a mix of chaos and order. This would be so poetic and reflect how life seems to work, especially for us humans. It strikes a deeper chord for me. And it isn't just having fun with the answers. It feels genuine, which without better science, I would not be comfortable running with. I just wouldn't want to say, we don't know and we'll know in the future when things get better. For right now, I just like the chaos and order mixture. And I think it's okay to go through life with thoughts such as this. It seems odd to me that people would just reject this theory with nothing to back it up except to say we've not found the keys yet to unlock the mysteries. But mostly, it's because of the answer's poetic nature. It is that wink from the universe that intelligent life is just supposed to happen. It's yin and yang, light and dark, chaos and order. It just makes sense in some wonderfully ineffable way. All right, everyone. One more little message from me to you. Just a reminder, if you'd like, you can go to remedialpolymath.com. You can read each article because it's written out beforehand. There are some visuals that might help you with this episode to understand things better. Another reminder to please, if you like the show, tell it to some people in your orbit and share the information on social media. And please like it and comment on whatever podcast app you use, but especially if you use Apple Podcasts. That would really help the show. Other than that, I really want to thank you for listening. And if you enjoy the music, you can write me at admin@remedialpolymath.com. And I'll send you the track. And I'm thinking about putting it up on Spotify and the like. So let me know if that's a good idea, if I should just put out all this music that I make, a track for each episode. All right, again, thank you so much for listening. Love y'all, and let's get to the ending of the show. Speaking of yin and yang, it's time to have some fun. I don't usually want to needlessly jump into woo-woo on this show, so let's just say we are jumping into some fun. While researching the tetrahedron, I was surprised to learn that Plato had also discussed it. It is considered one of the 5 quote-unquote Platonic solids. He wrote about it in his work Timaeus, almost 2,500 years ago. A Platonic solid is the shape in which all faces are identical, regular polygons. The same number of faces meet at each vertex, and the shape is convex, meaning it has no indentations. And there are only 5 of these shapes. The tetrahedron is unique in that it has the fewest faces, vertices, and edges. It is a shape studied for thousands of years for its mathematical beauty and symmetry. Interestingly, Plato associated it with fire. Isn't it cool that the shape water molecules like to form into has been considered beautiful and deeply thought about for a long time, well before humans even knew about molecules? I think it is. And it is another thing that just kind of weirdly makes sense, in an amusing way at least. In numerous Eastern cultures, the tetrahedron is interpreted as a symbol representing the balance between the divine masculine and feminine energies, referred to as yang and yin in Taoist philosophy. When it points upward, it symbolizes the divine masculine or yang energy, while representing action, direction, and initiation. When pointing downwards, it is associated with the divine feminine and symbolizes yin energy, receptivity, intuition, and nurturing. This duality is integral to many Eastern spiritual traditions, embodying the idea of harmony and balance in the universe. And of course, chaos and order is also an essential duality. In the world of sacred geometry, the tetrahedral represents a profound simplicity in the complex world of sacred geometry. It represents balance, transformation, and the pursuit of higher consciousness. It is said to be a reminder of principles that guide our path, change, stability, and the balance of opposing forces. That is also akin to chaos and order. Now, I am not pushing those ideas on you. I just find it intriguing and entertaining. Not only is the shape water molecules like to take one that has fascinated humans forever, but how water molecules arranged in their liquid state may poetically give it its anomalous properties. It's fun food for thought for about this vital molecule. Just as when its atoms are separated, it can blow up, but when together, can extinguish. Chaos and order, yin and yang, male and female, fire and water, life and death. Water can do both. Nay, it has to do both to give life. I don't care what anyone says. It's just some recreational quote-unquote science worth spinning one's wheels over at the end of an episode. All right, the conclusion. The hope for this episode is to make you wonder more about something you interact with daily. It isn't about woo-woo or fun stuff. It was to make you marvel at something you need to have every day, just as I did while researching it. It's endlessly fascinating to ponder that even the top scientists in the world still cannot explain why this world-covering molecule acts the way it does. I am not sure why, but I find it so genuinely fulfilling to be intertwined with this little bit of magic. I hope a bit of that fascination was transferred to you as well. Remember, quote, "Thus ice floats because we are here to witness it floating," unquote. It's 60% of you. It's essential to your DNA, and its peculiarities are necessary for life on Earth. Yet on some level, it's magic and hasn't given up its secrets yet. Yet, there it is. All right, I gotta go. Till next time, be well, everyone. All this talking has made me thirsty. Now I just have to figure out how to quench that feeling.